So last time we started talking about how to solve equilibrium concentrations using ice tables. We saw several different sort of approaches to solving those problems. One being obviously just sort of a perfect square situation. We also saw using the quadratic formula. We also saw at the very end that if your K value is relatively small, you can make an assumption. And the assumption that you can make is basically that X is equal to 0. And in that case, what we're doing is pretty much getting rid of all the X's except for really one. And it's all the X's that you would be subtracting from a number, all the X's that you would be adding to a number if that was the situation. Remember, though, that if we do make that assumption, we are going to be using, for our purposes, the 5% rule. And basically, the 5% rule means that the answer that you get for your X value, you take that number and you divide it by really the initial concentration that you're going to subtract it from or add it to, times it by 100%. And if it is 5 or less, then you are in good shape in terms of that. And you can obviously use that X value as the X value to solve the problem. If you happen to hit yourself there and it is not good in terms of 5%, it's more than 5%, then you really do have to sort of solve it a different way. And probably what that's going to mean is you're going to have to do some type of quadratic formula to solve it, would be most likely the route that you would need to take. Any questions in terms of the ice tables, how to solve them? That is like the big calculation of the season here in this class. Also remember that we could do it with concentrations. We also can do it with pressures. As I mentioned, I think the other day, if it is pressures, it does need to be in atmospheres when it goes into the ice table, regardless of sort of what is given to you in terms of the units or what you're trying to find. But you do definitely need to convert it into atmospheres before you put it into the ice table. Any questions on any of that there? Okay. So last thing I think we got going on in this chapter is Chateliers Principle. Maybe it'll come. Hold on, maybe. No, you could do it. Or not. There we go. So we're going to finish here talking about Chateliers Principle. Basically, this is an idea where we have a system that pretty much is at equilibrium. So with Chateliers Principle, we have this system that's at equilibrium. And then basically we do something to it. So it's at equilibrium, which means, again, that rate of the forward direction will equal the rate of the reverse direction here. And we do something to it. We add what is sometimes referred to as a stress to the system. Now, when we add a stress to the system, what that's going to essentially do is pretty much screw up the equilibrium. So we're no longer going to have the rate of the forward reaction equaling the rate of the reverse reaction. Now, when it does that, it's going to want to get back to equilibrium. So in order to get back to equilibrium, it typically needs to do one of two things. I guess there's three options, sort of. One option is to return to equilibrium. It needs to shift to the right, which basically means, obviously, it needs to make more products to get itself back to equilibrium. It could shift to the left, which means, obviously, the opposite there. It pretty much needs to make more reactants to, once again, reach equilibrium. And the other option that we'll talk about is actually one where it will actually be no change will occur. So they'll have like no change will actually occur, regardless that you sort of did something to the system, really will not cause a shift to occur. So what are stresses? What kind of stresses can we sort of add to this? It has a lot to do with concentration. So in terms of concentration, as we'll talk about, you can either add or remove concentration, obviously. When we talk about volume and pressure, they sort of go together. And when volume and pressure, we could either increase the volume We could increase the pressure, or vice versa, decrease the volume, decrease some pressure. And those things will cause some changes to occur in most cases. The other thing is temperature is another stress that we commonly can do to it, which obviously means we could either increase the temperature or we could decrease the temperature. And one last thing, as we'll talk about, which in the end really doesn't make too big of a deal, but we could add a catalyst to it. Catalyst, again, is something that's added typically to speed up a reaction. It's not really a reactant. It's not a product. It doesn't get used up in the reaction. It's there really just to, in most cases, facilitate the reaction to occur faster. There are negative catalysts, which will allow the reaction basically to occur slower. But most of the time when we talk about a catalyst, it is usually in the reference of it sort of speeding it up. So we have, again, the system at equilibrium. We do something to it that really kind of screws up the equilibrium. The system itself will readjust to try to get itself back to that equilibrium position. Will we have the same amount in terms of equilibrium position at the beginning and the end? No, but again, we will have the same ratio of products to reactants. That equilibrium constant will be the same once it does reach equilibrium there. Any questions on that there? So let's take a look at some of these here. Let's start with concentration. So in terms of concentration, this will sort of follow what's in the notes, I think. In terms of concentration, as I mentioned, we can pretty much do one of two things. We could either add or we could remove. And when we add more, it typically will cause the equilibrium to shift away from the side you added it to. So AA is a good way to remember that. Add away is basically what will happen in that case. And if we remove something, it will shift towards the side we removed it from. So to sort of demonstrate this sort of concept here, let me do some award-winning drawing here. So let's say we had a nice system here at equilibrium. And we had some stick figures here. This is advanced stick figures. They have faces. There we go. That's the second part of the class. There we go. And we'll say the guy on the left here is the reactant side. Guy on the right is the product side. And we'll say these guys are at equilibrium at this point. So they're happy, they're at equilibrium, and everything happens. Let's say that we decide, well, we're going to pop somebody on to this side of the seesaw there. When it does so, this is what's going to happen, right? It's going to weigh down that side. And what we will see is a couple guys on this side, still happy on this side, maybe not so happy on this side, right? Now, in this particular situation, in order to fix that, we need to put more people on the left or more people on the right. Yeah, so we added to the right-hand side. The equilibrium needs to shift away from the side we added it to and put more people over there on the left-hand side. And once again, it will come back to equilibrium here. Position. And we're back to that sort of second equilibrium. So we added, it had to shift away from the side we added. Essentially what it's doing is we add more products, it's going to make the reverse reaction kick into gear, right? And it's going to start making more reactants and shift to the left. And that's essentially what's happening in that case. Now, if we have the same sort of equilibrium we started with here, again, same idea, guy on the right there is our products. Guy on the left, there's our reactants. And let's just say this guy over here hops off. And when he hops off, what's going to happen is this is going to happen. And in this particular case, to fix this, we need to put more people on the right-hand side. So we remove from the right-hand side, the equilibrium will shift towards the side we removed it from. And once again, it will come back to equilibrium in this particular case. And of course, the life lesson here is do not sit on this side of the seesaw, right? That seems like a bad side to sit on. Same idea here. What's going to happen is essentially we're going to remove products, which means we really have more reactants, which means we got plenty of reactants to do the forward direction, right, in this particular example. And that's going to send the reaction towards the product side to make more products. Any questions on that there? By the way, adding something should be pretty easy. If we want to add something to a reaction, we simply just need to grab it off the shelf and dump it in, right? How do we remove something? Do we reach in and just grab it? Not a good idea. You shouldn't reach in and grab it. How do we actually remove something from a solution? What are some ways that we can do that? Any ideas? So we have a solution. It's happy. We have some ions maybe flying around in here. And I want to remove some of these things. One way you could do that is you could add something to it that might react with one of those guys and create a solid, right? You could create a precipitate. When I create a precipitate, that's like essentially reaching in there and grabbing those ions out of the solution, right? We also know our solids included in the equilibrium. They are not, which means we're pretty much taking it out of the equilibrium, right? So we're taking it out of solution, and that's obviously a very common way that we can sort of remove something from a solution. We could visually see that, obviously, right? We could visually see the solid being made, which would be removing, again, some ions from there. Another way we could remove something which might not be as visual is, let's say I had a solution where there's hydroxide floating around. What would happen if I add an acid to it? Yeah, because acid pretty much is H plus and OH minus will form water, which is a liquid. Is that part of the equilibrium? That is not. That's essentially like removing hydroxide out of that solution. Probably won't visually be able to see it, right? Because you're like, hey, I made water. Exciting. But essentially what you're doing is you can remove hydroxide. So if you have any type of solution where perhaps there is hydroxide, there's hydronium ions, H plus floating around, you could add an acid or a base, you could form water. That, again, is another way that you can remove something from solution. Any questions on that? Now, clearly, when we talk about one side of the reaction or the other, we are clearly speaking of the actual equation when we look at it, right? So we're talking about, you know, what's in the equation. You know, if this is A plus B goes to C plus D. If I add more D, it's like adding more products, right? If I add more A, it's like adding more reactants. In this particular case, there really is no left or right-hand side of the beaker, right? If it's in solution, everybody's floating around. It just means when you add more, it will make more reactants or products because it's forcing that equilibrium one way or the other. So when we sort of answer these Chateliers Principle questions, we sort of think of left and right in terms of the reaction or the equation, the way it's written. Clearly in the beaker, there is no left or right. All that stuff is really floating around in there to start with, right? Everything's in there. Kind of like the solutions you made last week, right? Your unknown solutions, you put some iron, you put some thiocyanate, you let it hang out for a bit, which meant you made some product. So really in that beaker or that test tube, wherever you put your solution, you had everybody in there, right? And you can either add more to it or remove some stuff. Any questions on concentration, how it works? All right, the next thing we'll talk about then is we'll talk about volume and pressure. And really these guys, for the most part, are sort of tied to one another. And as you might remember from gas laws, our good friend Boyle, right, said that as the volume goes up, what happens to the pressure? Pressure goes down, right, that inverse relationship. And as the volume goes down, the pressure goes up. So when we're dealing with the idea of volume and pressure, especially with gases, personally, I like to focus in on this guy, which is volume. And understanding this relationship will help you sort of understand what is going on. So if we increase the volume, that means that the pressure is going to drop, which means in a larger volume, would we need more or less gas molecules to help out the pressure? So if you think about it, the change that we're seeing is the pressure is coming down, which means essentially we want to kind of bring the pressure back up. In order to bring the pressure back up, do we need more or less gas molecules to do that? We need more, right? Bigger volume, more gas molecules, more collision, more pressure, right? That will sort of compensate for the change that we saw, bring the pressure, back to equilibrium. So it will shift to the side with more gas molecules. And that is really, dependent on the actual equation you're looking at, or reaction. You have to look at the equation and see on the left-hand side how many gas molecules you have, right? And on the right-hand side, how many gas molecules you have. You basically find everybody with a G, and you add up their coefficients on each side, and that will tell you how many gas molecules you have. Opposite is true. Smaller volume, pressure starts to increase. And in this case, again, if you just sort of think about it in terms of volume, smaller volume, you need less gas molecules there. Again, with a smaller volume, pressure starts to creep up to sort of bring it back down to where it was originally, or in that idea of equilibrium. We actually need less gas molecules. So in this case, it will shift to the side with the least number of gas molecules. Any question on that? So, if we have something like, we'll do 2A plus B goes to 2C. So let's say in this case, we added more C. We removed B. We decreased the volume, and we increased, actually we'll do decreased the pressure. All right, take a moment and decide in this case, will it shift to the left, the right, or will there be no change? All right, take a second and see what you come up with. All right, let's take a look. So here, if we add more C, what should happen? Should shift to the left. So C, if we look at the equation, is over here. When we add, it shifts away from the side we added to, so it should shift to the left in that particular case. What happens if we decrease the volume? Yeah, so in this case, it would be this situation. Decreasing the volume means increasing the pressure. Again, if you just kind of focus in on the volume part of it, smaller volume means we need less gas molecules in that case. On the left-hand side, how many gas molecules total? Yeah, 3 gas molecules. Right-hand side, 2. Again, simply just count the coefficients, right? 2 and 1 is 3, and just 2 here gives you 2. That means, again, in this case, we would shift to the right-hand side, as that is the side with the least number of gas molecules. Any questions on that one there? If we remove B, yeah, if we remove B, B is on the left-hand side of our equation. When we remove, it goes towards the side we removed it from. And again, it's going to go to the left-hand side. Again, the idea here is we're kind of making the reactants deficient. We have a lot more product at that point. That's going to basically initiate the reverse reaction from happening in that particular case. Lastly, if we decrease the pressure, we should expect it to shift which way? It should shift to the side with more gas molecules, because a decrease in pressure means an increase in volume, and we need more gas molecules to fill up that bigger volume. So it should shift there to the left. Any questions on any of those there? Okay. So that is volume and pressure. That is concentration. So that leaves us, I think, here temperature to sort of talk about in terms of Le Chatelier's principle. So let's talk a little bit about temperature. And temperature basically works the same way as concentration. And because it works the same way as concentration, that means if we increase the temperature, it will shift away, just like concentration. And if we decrease the temperature, it will shift towards the side. So which side are we talking about here? Well, it really depends on what type of reaction you're dealing with as to whether it is a endothermic reaction or exothermic. If it's an endothermic reaction, a couple of things, typically delta H, which is the enthalpy of the reaction, is typically given to you. And basically, if it's endothermic, I think we talked about it earlier, but just to remind you, that would be a value that is a positive value for delta H. And really, the number doesn't matter. It's actually the sign. So if you have a positive value, that would be a endothermic reaction. And if we think about sort of a reaction that is endothermic, if we had to put the heat or energy into the equation, basically it would be a reactant. So it's considered a reactant in this case, absorbing energy. So it would be on the reactant side. And if it's exothermic, that means that the delta H would be negative. Heat and energy is being released in an exothermic reaction. And just like the other, we think about heat and energy in this case as a product. I should actually write it in there on the product side. So we think of it as a product. And again, that means if our reaction is endothermic and I increase the temperature, which way will it go? If it's endothermic, I increase temperature. It should go to right. Endothermic means heat's over here. It'd be like adding more reactants, which would make the shift away. If I put everything on ice in an exothermic reaction, which way will it go? Like throw all my test tubes on ice. Would it go to the right or left if the reaction is exothermic? It would. So exothermic means heat and energy is a product. And if we put something on ice, that is like removing heat and energy. And that is like taking the heat and energy away, which means it should shift towards the side you removed it from. Vice versa on both of those. If you increase the exothermic, it should go to the left. And obviously, if you increase the or remove the endothermic, it should go to the left. Most of the often in our situation, the way you'll be determined if it's exothermic or endothermic, if you're given an equation is they typically will just lay up the delta H value after the equation. And again, like I said, it's really not important. The number is actually the sign that's really important in terms of this stuff. Any questions on that? By the way, if I change the temperature, what happens to my equilibrium constant? Does it stay the same? It doesn't. So remember, that's the one thing that will actually change the value of the equilibrium constant if you change the temperature of it. Any question on temperature? Yeah. Not necessarily, as long as, you know, the things, for example, in the same room, overall, the temperature of that container probably will remain relatively constant. Yeah. Yeah, so you would need to know whether it's exothermic or endothermic. So I would think they would have to give you some type of information. Now, mind you, if you don't have information and you're like physically doing an experiment, for example, let's just say we're doing an experiment where like this side is more red and this side is like green, right? And you don't know if it's endothermic or exothermic, right? But you do the reaction and you you do the reaction and you increase the temperature, for example. Let's just say we did this reaction. We put our test tubes in a hot water bath, right? Increase the temperature and all that good stuff. And it shifted and turned green in the test tubes, right? So it was maybe a color in between and it turned green at this point. Would that tell you it's endothermic or exothermic? Well, let's see. So it shifted this way, right? Obviously, right? Now, in terms of temperature, what are the two ways I could get it to go to the right? If it is a exothermic reaction, right? And I removed temperature, which is not what I did here, which way would it go? So if it was exothermic, this reaction, and I removed energy and it went this way, it would mean that, it would be exothermic. I didn't do that, right? I didn't remove energy in my example. I actually increased it, right? So that would mean that this reaction would actually has to be increased here, shift this way, right? If it was exothermic, I increase here, shift to the left, which means I should see it red, right, in the test tubes. But I saw it turn green, which means it's actually going to be endothermic. So in an actual experiment, if you have sort of colors on both sides and you increase the temperature, decrease the temperature, depending on which way it shifts, you could actually figure out whether or not the reaction is endothermic or exothermic. So again, in this example, if I increase the temperature and it shifted and turned green, we know it shifted to the right. The only way to get it to go to the right by increasing the temperature would mean it has to be endothermic to do that. It has to shift away from that side. Again, if it was exothermic over here, it would have turned my test tubes red if I increased the temperature. So you can look at something like that and determine if it's exothermic or endothermic. Other than that, they would definitely have to give you some type of piece of information in a book type problem. And that, like I said, very commonly you'll be given the delta H value, or they may just lay up heat or energy on the reactant side or product side, which obviously would tell you, again, if it's on the reactant side, it's endothermic. If it's on the product side, it's exothermic. Other questions on that? The last thing is a catalyst. A catalyst basically will speed up the reaction, but it will really cause no change. So one acceptable answer in Chateliers Principle is no change. And one way you could achieve that is if you add a catalyst, you'll just get there quicker. It won't really cause it to shift one way or the other. Other things that you could add that will sometimes cause a no change is like a noble gas, right? They're chemically inert, so they could fly around and really not cause too much damage in that particular case. Question on any of that there? All right, so we've got some examples here. We'll look at some. So here's what we talked about here. Again, should have followed, hopefully. Concentration, again, shift away or go towards removed. K will change depending on the temperature, but again, we think of it works really the same way as concentration and pressure. Again, adding inert gas will not cause any shifting, but decreasing the volume or increasing the volume, which results in changes in pressure, obviously will cause changes. So let's take a look at one here. Let's say we got this guy there. That missed badly. There we go. We'll do this. And let's say that the delta H here, probably not correct. I'm just going to make up a number just for this illustration purposes. We'll go with negative 175 kilojoules. So answer these questions. Will it shift to the right? Will it shift to the left? Or will there be no change? If we add more and 2, decrease the volume, remove NH3, increase the temperature, add a catalyst. Let's go with increase the pressure. All right, take a minute or two. All right, let's take a look. So starting with our first one here, if we add more N2, which way should it go? Should shift to the right. Again here, N2 on the left-hand side, that's going to basically feed the forward reaction to occur, cause it to shift to the right. If we increase the temperature, which way should it go? So what type of reaction is this, endothermic or exothermic? It is exothermic. We know that simply because there is a negative sign there. That's all we need to know. That basically means that if we added this in this made up example here, heat would be considered a product. If we increase the temperature, that would be like increasing the product side, which means it should shift away from it and should head to the left there. Yeah. Any questions on that one there? If we decrease the volume here, what are we looking at? Okay, so if we decrease the volume, we want less gas molecules in there. Left-hand side, we got a grand total of 4 gas molecules, looks like. Right-hand side, we got 2. And that then would mean it would definitely shift there to the right-hand side, less gas molecules. Again, just simply adding the coefficients for anything that has gas next to it. We add a catalyst. No change. If we remove NH3, it should go to right. Again, we're going to remove products. Removing products is going to make really products deficient, going to increase the forward reaction, right, to kind of fill that void. And we would expect it to go towards the side we removed it from. Lastly, increasing the pressure should send it, also send it to right. It's really the same thing as this, right? If we increase the pressure, we're going to decrease the volume and need more guys there on the right-hand side. Any questions on that? Yeah.
For N2,
yeah.
For add more N2,
Mhm.
why would it be? Because I have shift away from the side you added.
So whenever we add more of anything, it does shift away from the side we added it to. So in this particular example, N2 is over here. So basically what's going to happen is when you pile on more N2, kind of like we talked about at the very beginning of the chapter, having that more N2 there is going to increase the rate of reaction of the forward direction, right? The H2 doesn't have to go move around to find N2. By those guys increasing, it's going to basically kickstart the forward direction in that case, which means it should shift away from the side we added from. If we added more NH3, is that what we said? Yeah. If we added more NH3, it would shift to the left for the very same reason. By adding more, if we did to this side, you're basically piling up a ton of products, which they're just going to start reacting at that point, and that's going to cause the reverse reaction to occur, and it will shift away. So that's why those guys shift away. When you add more, you're basically just fueling whichever side you're adding to, the forward reaction or the reverse reaction, to basically kick and get going on there. Yeah. Take a look. So again here, we're going to decrease the temperature. So clearly they tell us it's endothermic. That means, by the way, my delta H value would be positive or negative? Would be positive. Also means that if we think about the heat and energy, it should be considered a reactant in that case. Now, if we go to decrease the temperature, that is essentially removing heat and energy over here on our reactant side. That should cause it to shift towards the side we removed it from, as it works just like concentration. And we should see really the reverse reaction sort of kick into place. Again, same idea, you're sort of depleting the reactants. That's going to cause that reverse reaction basically to sort of predominate at that point. If we increase the volume, what happens? It would be no change in this particular case. Here, we would look at gas molecules. That is 2 on this side. And with the actual 2 that should be there, that is actually 2. That is what we call a tie. There is no more or less. So actually, this would be another way that you could kind of achieve a no change when you have kind of equal amounts of gas molecules on both sides. Any questions on that there? Adding NO should cause it to shift. Should cause it to shift to the left. Again, adding more on our product side will increase the amount of products, and that will again kickstart the reverse reaction from happening. If we remove O2, it is going to go into the left. Again, when we move, it goes towards it, depleting the reactants, again, causing that reverse reaction basically to occur. Increasing the temperature then means it should go to the right. In this case, we've established that it is endothermic. So if we increase that guy at that point, should cause everybody on this side to basically start reacting and cause it to head to the right-hand side. Add N2 is going to cause it to go to the right-hand side as well. Again, same reason, more reactants is going to cause an increased rate in the forward direction of that reaction taking place. And adding helium will do no change, yeah? Any questions on any of those? Yeah, so if we looked at, like, if we increase the pressure, right? Increase the pressure basically would do the same thing, drop the volume, but in this case, again, we have two gas molecules on both sides. And well, it's kind of like if you remember those couple of questions we did at the very, very beginning of the chapter, you know, when we said, hey, we're going to add more H to this reaction or something like that. So it's kind of the same idea. It really was the Chateliers principle we were talking about back then. We just didn't know it. So to answer your question, like we talked about, if we added more N2 was your question, right? What happens to the O2 concentration? Because we added more N2, the O2 is going to be able to find it pretty quickly. And again, that is going to kickstart the forward direction. The result of that is, as we kind of talked about in those earlier examples, we would expect this concentration to start to go down, right? Because that's the only way we could go to make products. Just like at that point, we would expect this concentration to start to increase, right? In terms of the N2, kind of like what we answered when we did those questions early on, we would expect it probably to go up, and then as it starts reacting, it should start coming back down. So again, because you artificially added it, it may not come down actually higher than it started, and that's only because you went and dumped more in there, basically. But the kind of pattern you should see in that case of N2 it should peak, and then as it starts reacting with O2, O2 should come down, and the N2 should come down as well. It's just you sort of artificially inflated the N2 concentration at that point. Other questions on that? Questions on Le Chatelier's principle? Yes. All right, that wraps up this chapter, whichever chapter this is. 13, 12, 12, 12, sounds good. I think we should do a quiz next Tuesday on this chapter. Feels good, feels strong. I think we'll do it at the beginning of lecture on Tuesday. It will be on here. No formulas will be provided to you, but again, any type of constant values and that type of stuff obviously will be provided for you. You need something to write with, and a calculator, probably mostly problem-based would be my guess. Any questions on that? So we'll do that at the beginning of lecture on Tuesday. So I don't forget to give you a quiz this semester. We did one quiz and you got to drop your lowest. That's cool. All right, so we'll do that, and then we'll continue lecturing obviously afterwards. Any questions on that? Okay. Then we're off to, I believe, chapter 13, which is some acid and bases here. So we're off to chapter 13, which is acid and bases. And this is our beginning journey into the wonderful world of acid and bases. And we're building up to, you know, the next couple of chapters, which again, as we talked about early on, sort of the peak of the class here. So in this chapter, we're going to go over maybe some stuff that you remember from acid and bases if you took whatever they call that pre-class nowadays, 100. I think that's what they call it. I don't know. I'm so old, they used to call it 209 when I taught it years ago, but I think they call it 100 now. And we're going to talk about acid and bases. We're going to talk about pH. We're also going to talk about what happens with weak acids and weak bases and polyprotic acids and stuff like that. So let us get going on some of the basics here. Obviously, acids and bases, they do have certain sort of characteristics that you're probably familiar with. Good talk. All right, so acids, they have a sour taste. Clearly don't taste any acid or bases in the lab. You should be wearing your mask, so you shouldn't be doing that anyways, right? But, you know, vinegar basically is acetic acid. Fruits have citric acid. They react with certain metals to produce hydrogen gas, and everybody's favorite reaction, which is, what type of reaction is this guy? A little hydrochloric acid action, right? This is a Not everybody at once. Okay, just anybody at once. This is a, there you go, single replacement reaction, right? Zinc comes in, kicks out the hydrogen there in the acid, as they say. Hydrogen gets popped out, comes out as hydrogen gas, bubbles, all that good stuff. All right, single replacement. In order for zinc to come in, zinc needs to be more or less reactive than hydrogen. It does need to be more. So whatever comes in on a single replacement reaction needs to be more reactive than what it is replacing. Otherwise, it will not occur. So if you swap that out for some copper there, good luck on that. That's not going to work very well for you. They also react with carbonates and bicarbonates to produce carbon dioxide gas, and another reaction that you're probably familiar with, maybe a little sodium bicarbonate, a little baking soda action. Double displacement reaction here makes H2CO3, bless you, plus some sodium chloride. This acid is carbonic acid, right? Which quickly goes through a decomposition reaction, produces CO2 and water, right? Plop, plop, fizz, fizz, Alka-Seltzer. Kind of the same idea. Many bases feel slippery. A lot of soaps, Drano, those type of things are bases. A lot of our strong bases come from group 1 and group 2 on the periodic table. Group 1 is what, guys? Those are the alkali metals. Yes. Group 2 are the alkaline earth metals. The word alkaline means basic. Yes. So alkaline means basic, and that is where a lot of our strong bases come from. Also, just a reminder of nomenclature, right? We remember how to name acids rather than that thing, right? By the way, when we name acids, it all revolves around oxygen is the big deal, right? And if the answer is your acid has no oxygen, it starts with hydro, something ic acid, like HCl, no oxygen, hydrochloric acid, right? HBr, no oxygen, hydro, second guy is the anion, which is bromic. So that is hydrobromic acid, right? What makes something an acid is H plus is the cation, right? In all cases, the anion is something different. If the answer is yes, my acid has oxygen, it will have one thing in it usually, and that is everybody's favorite thing. That is the polyatomic ion, yes? We remember that those polyatomic ions end in two ways. Typically, they end in 8 or ite, right? Those are typically the two ways that they end. If your polyatomic ion has oxygen and it ends in 8, your acid is something ic acid, like HNO3. NO3 minus is nitrate. This is nitric acid, right? H2SO4. SO4 is SO4 2 minus, which is sulfate. This is sulfuric acid, right? And if your polyatomic ion will come this way, ends in ite, your acid will be something OUS acid, like HNO2. NO2 is NO2 minus, which is nitrite, ITE. This would be nitrous acid. If you got oxygen in your acid, there is no hydro. Yes, hydro only for guys that do not have oxygen. Why do we put aqueous here for our acids? That is basically what makes it an acid, right? An acid is basically a solution that has H plus floating around and some type of negative ion floating around with it. And that occurs in like a solution, which is why it's aqueous. Because if we had HCl that was a gas, what would we call it? Hydrogen chloride gas, yes? You take hydrogen chloride gas, you bubble it through water, you get hydrochloric acid, yes, in that case, which makes a solution. Any questions on your 1 minute review of nomenclature of acids? Yes? I know, it's kind of like the original lecture I gave. I know, it's all right. That's all right. You don't need days to learn these things. All right. So let's talk a little about some of the early definitions of acids and bases. Sort of an early definition of acid and bases was one done by Arrhenius. He did a lot of work with electrolytes. Electrolytes, right, are solutions that basically conduct electricity because they're able to produce ions in solution, right? Strong electrolyte 100% breaks apart, produces a lot of ions, conducts electricity really well. Light bulb goes on very brightly. If you've ever seen that experiment where they stick an electrode with a light bulb in a strong electrolyte, light bulb very bright. A weak electrolyte is one where it mainly stays together, but does produce a few ions. So if you put your light bulb in that, it will come on, but be very dim. Then we have non-electrolytes, which do not conduct electricity because they really don't produce any type of ions in solution. So he did a lot of work with electrolytes and a lot of work with acids. And he basically called an acid anything that has the ability to produce H plus or H3O plus in solution or water. In acid-base chemistry, pretty much H plus, which is the hydrogen ion, are sometimes referred to as a proton. Why is it referred to as a proton? Hydrogen has how many protons? How many electrons? It has one electron. How many neutrons? 0. Yes. In order to become positively charged, you have to lose an electron, which means this guy is left with just a proton, right? This is why it's sometimes referred to as a proton. H plus is basically, for all intents purposes, the same thing as H3O plus, which is the hydronium ion. Hydronium ion. And the hydronium ion, which is H3O plus, is basically like a polyatomic ion. Oxygen in the middle, 3 hydrogens attached with an overall charge of +1, sort of happening. You could interchange H plus and H3O plus in equations, in formulas. I personally will usually roll with the H plus, but anywhere I put H plus, you could pretty much put H3O plus, and it's basically kind of the same thing. You might be asking, you know, how do you get H plus versus H3O plus? The way is like this equation here. This is really just hydrochloric acid dissolving in water. And basically, if you include water, it does a double displacement reaction where the H plus comes over here and the Cl minus is left over, and then we form H3O plus. If you choose to write this equation, which you could write exactly like this without the water included, it will look something like this, H plus and Cl minus. Both of these equations are identical to each other. The one on the bottom does not have water, and you just make H plus. It's basically just breaking apart. If you want to put the water, it's 100% correct, and you will produce H3O plus. They're basically equivalent to each other, both of those equations. And again, you could interchange H plus and H3O plus along the way. He described basically a base as something that has the ability to produce hydroxide or OH minus in solution. So these are really, you know, the basics of what is something that is an acid and what something a base is. It's also the basics of when you write your equations properly for you to know if you're dealing with sort of an acid solution or a basic solution based on what you see on the product side. On the product side, if you see H plus or H3O plus in your equation, it's probably like an acid situation happening. If you write an equation, you see OH minus on the product side. That's a big hint that it is a basic situation going on. Super important in this chapter, next chapter, and several chapters down the road to properly be able to write these equations, because if you're able to do so, it will help you out with the calculation part by going, I see H plus, I should be doing like an acid calculation here, or I see OH minus, I should be doing a base calculation. So as we talked about, I think at the beginning, it's really important to be able to write equations correctly, and it can give you a lot of information or clue as to how to approach the math part of it. So again, keep that in mind as we kind of go through these guys. Any questions on that there? Now, that was a pretty good definition. It was sort of limited as he really did focus in on a lot of bases that did contain hydroxide in the actual formula. Along came more of a general definition. I don't know why on this slide our good friend Lowry gets kicked off all the time, but this is the Bronsted-Lowry definition. The Bronsted-Lowry definition of an acid is a proton donor. So that is something that's going to give an H plus over. That's really important because remember, it is not just an H, but there is a plus aspect of it. That makes a big difference in terms of charges and stuff that you end up with. Sometimes people just focus in on the hydrogen, but the charge does make a difference. A Bronsted-Lowry base is something that will accept a proton. So again, it's going to accept an H plus, also really important in terms of the overall charge. In this particular case, what's happening is we have NH3, which is ammonia, not ammonium, but ammonia. And it is actually a base, which means what's going to happen is the water here is going to act as the acid, is going to send our proton over there. This is going to act as our acid. This is going to act as our base. The result of the Bronsted-Lowry definition is we get actually some pairs on the other side. We get NH4 plus, which is known as the conjugate acid. And we get OH minus, which is known as the conjugate base. This is considered a base because it's able to produce hydroxide here, right? Which is basically our definition. And we see it's really coming from NH3, which does not have actually hydroxide in its formula, but it's able to produce hydroxide. And by the way, we see arrows heading in both directions in this case, which tells us that this is actually a weak base ammonia because of that. So ammonia is actually a weak base. There is a relationship between the acid and base and the conjugate acid and base. The base on the left-hand side is partnered with the conjugate acid on the right-hand side. The acid on the left-hand side is partnered with the conjugate base on the other side. The only difference between the two sides is a H plus. The only difference is one H plus, since it is basically given away one at a time. And that is how we can figure out what are sometimes referred to as acid conjugate base pairs. The only difference that there can be is one H plus. If there's anything more than one H plus, they are not pairs. They are not related to each other in that sense. It has to only be one H plus. Again, because we have really the transfer of that H plus from the acid to the base. Any questions on that there? The only difference you could have, so these are what are referred to as acid conjugate base pairs. And that's basically the relationship of the guy on the left to his like partner on the right. The only difference is one H plus. That's the only difference there can be. So what I mean by that is if we look over here at NH3, its partner on the other side is NH4 plus. So if we just look on the left-hand side, we have NH3, right-hand side, we have NH4 plus. The only difference between these two things is that H plus that was accepted. Yeah, so it has one H plus that was accepted, one more H plus than it started with. Same thing if we look at water on the left and we look at hydroxide on the right. The only difference between those two things is the same H plus basically, and it has one less H plus between those two. This and this is what's referred to as a acid conjugate base pair. The NH3 and the NH4 plus is what's referred to as a base conjugate acid pair. Again, they are related to each other by the lonely H plus that is being transferred from one to the other. So that's the difference between them. So if you had something that was a difference of more than one H plus, they would not be considered a pair. Other questions on that? Okay. Sorry, I scribbled on there, I think. All right, so let's take a look here. For each of these listed, are these conjugate acid base pairs? So see what you think. The conjugate acid base pairs is really, this is what you're looking for, is the difference basically in H plus. That is basically what you need to look at. So in comparing our first one here, we have HCl and OCl minus. The difference here is an H plus, but it's also a oxygen, right? That's like hypochlorite, right? And that is HCl. These two guys would not be a pair because the difference is more than just an H plus. Although it is an H plus difference, there's also that oxygen that's a difference. So they would not be pairs. How about number 2? Are those guys pairs? H2SO4 and SO4 2 minus. The answer is no, because the difference here is actually 2 H pluses. So these guys also would not be pairs. NH4 plus and NH3, which we just saw, is a pair. The only difference is 1 H plus between those two. You can either put the H plus on the NH3 and you get NH4 plus, or you take it off the other guy and you get this. So it looks like a winner so far. H3O plus and OH minus, are those guys pairs? They are not. Again, here we're looking at like a 2 hydrogen difference that's going on here. So those guys, again, would not be pairs. Clearly, none of these are wrong. So looks like only 3, number 3 there is a pair, yeah. Now you may be asking, H2SO4, SO4 2 minus, they seem like, they should be a pair. They seem related to each other. And the answer is they are related to each other, but they are not related to each other by the definition of conjugate acid base pair. H2SO4 is what we call a diprotic acid. Di meaning 2, protic meaning protons. It has 2 protons to give, basically. They actually do not come off both at once, even though we commonly think about it that way, like in the first semester of our course here. You probably think about, well, it's H2SO4, it's going to give off 2 H's. They pop off both at the same time. They actually occur one at a time. So when an acid has multiple hydrogens, they lose it one at a time. And what first happens is the H2SO4 will basically drop a hydrogen and become HSO4 minus. The next step is that HSO4 minus will drop the second hydrogen and become SO4 2 minus. That is why when we look at this in terms of pairs, this guy and this guy, they are pairs because the difference is 1 H plus. This guy here and this guy also pairs because there's 1 H plus difference. Going from H2SO4 directly to SO4 2 minus is too many steps along the way. We sometimes think about both of them coming off at once because in the previous class, you just looked at the overall reaction, which means if you add these together, this cancels, this cancels. The overall reaction we look at is H2SO4 goes to 2 H pluses and sulfate, which is why we sometimes think of them both just coming off at once. That's actually the overall reaction that happens. It's actually a stepwise dissociation with those hydrogens coming off basically one at a time. Any questions on that there? Okay. All right, so let's take a look here. C6H5NH2 is isolated, blah, blah, blah. What is the formula of the conjugate acid here? All right, so hopefully you know that it is an H plus difference. The key is, the big question is, should you put the H plus on or should you take the H plus off? So this is where sort of thinking backwards is sometimes helpful. If you remember, we saw the equation. Basically, we have an acid plus a base. And by the way, the acid and base, regular acid and base, always on the left-hand side of the arrow. Your conjugate acid and your conjugate base on the right-hand side of the arrow. The relationship is acid on one side, conjugate base on the other. Base on one side, conjugate acid is the relationship, which means in this particular case, they were nice enough to tell us that it's a base, but if they didn't, and they just said, what is the form of the conjugate acid, we could look here and know if we go backwards, what we are dealing with are bases. So that's a way you can kind of think of it backwards. And basically what that means, all we need to do is do what the definition of a base is, which the Bronsted Lowry definition of a base is. H plus gets, so a base will accept an H plus, right? So we're going to actually put the H plus on here. And that means that we simply just do just that, put the H plus on, and we end up with something like that, which looks like number 2 there, I think. So sometimes it's helpful to think backwards. If you're asked to do the conjugate base, that means you're starting with an acid, which means the acid should donate the H plus. If you're doing the conjugate acid, that means you're starting with a base, which means the base should accept the H plus. Any questions on that there? All right, so finish up on here. We have, say, HCO3 minus. Why don't you write the conjugate base? And why don't you also do the conjugate acid for it? All right, so we're getting to the end here. So let's take a look. We'll do the conjugate base first. So again, using my philosophy here, if this is the conjugate base we're looking to do, that means if we follow the arrow backwards, in this particular case, our guy here is going to act as an acid, which means it should donate an H plus, which means we should end up with CO3 2 minus in that particular case. Any questions on that one? If we want the conjugate acid, again, kind of following the same logic. If we're looking to do the conjugate acid, that means in this particular case, this guy is going to act as a base, which means the definition of a base is something that will accept an H plus, and we will end up with H2CO3, yeah? Carbonic acid. Any question on those two? This is something right here, right, that can act as a acid or a base, and those things are what are known as being amphoteric. An amphoteric substance is something that can act as an acid or a base. Typically, you find a lot of these guys that look like this, they got a hydrogen, they got a negative charge. They could kind of go both ways, if you will. That's a lot of guys that has the ability to do that. Water, by the way, has the ability to do that. It can act as an acid or a base and go either way as well. Any questions on that or anything we talked about? All right, we will stop right there for now.